So, let us take today the carboxylic acid derivatives. Derivatives means derived compounds. So, we have carboxylic acid actually RCOOH. This is what called the carboxylic acid. In this the OH is suitably replaced by the 4 different types of the groups. If it is treated with reagents like PCl5, let us say, then you will get a RCOCl. You can have a bromo and the iodide also, but commonly the RCOCl is the general the acidic halide. This is called up to this you say alk oil chloride, alkanoyl chloride. This is called commonly acid chlorides, acid chloride. So, by replacing the OH with Cl, we get acid chloride. This is the one derived product of the acid. Similarly, you can have a by heating strongly with the presence of P2O5, if you heat it, 2 acids will join. That means, in the place of OH, we get a OCOR. So, this is the new group entered in the place of the OH. Here the Cl is the new group. So, RCOCl, another acid entered, actually 2 acids lose water. So, one water molecule is taken by P2O5. This is called up to this again it is called alk alkanoic anhydride, alkanoic anhydride, or commonly known as acid anhydrides, acid anhydride. This is the second one. Similarly, when you treat it with alcohol in presence of generally with a sulfuric acid and then slightly warm it, this OH is suitably replaced by the RCOOR. So, an alcohol has come. So, alcohol containing acid, this is called this is again this is alk main compound. This is newly entered. So, therefore, first we finish off this by saying alkyl. So, this alkyl is actually this R is finished by saying alkyl, then say the main compound alk ANO8. This is what IUPAC nomenclature. There are 2 alks are there. The main alk is our acid, this is one. The R is later entered, therefore, just like extra group we finish off this alkyl, alkane OH. Number of carbons will decide what is that alkyl. So, this is called acid ester, commonly known as acid ester. Lastly, there is one more derived product, that is when you treat it with ammonia followed by strongly heating. First add ammonia, you get a salt of the acid, ammonia salt, just like sodium salt, potassium salt, you will get a NH4 plus RCOO minus, the salt is formed. Go on, heat it, that salt melts and then distill out as a RCONH2. So, their preparation is from the carboxylic acid. In fact, they are all derived from by replacing the OH, therefore, they all are called acid derivatives, and this is called now again alk, systematically alk amide. So, depending upon the number of carbons, including the carbonyl carbon, always in the acid also including the carbon, we say alkanoic acid. Like that, in all this including the carbon, number of carbons will decide this what is that alk. For example, if the hydrogen is H, this is 1 carbon acid, therefore, methanoamide, ethanoamide, propanamide and so on, commonly known as acid amide, acid amide. So, there are 4 derivatives are there: acid chlorides, acid anhydrides, acid esters and the acid amides. All they are formed from the carboxylic acid, therefore, they are called acid derivatives. Each one has got its own individual the reactions and the applications. However, there is some continuity or the interrelation between these 4 derivatives. That first we will take that what is the interrelation or the how they interconvertible, in fact, how they they react, that is reactivity order or stability order together, we will see. Then we go to the individual member acid chloride, its preparation and applications are the properties of acid chloride. Like that, each derivative we will take up later. But first let us see what is that interrelationship or relative reactivity of these 4 derivatives with reference to the carboxylic acid also we can discuss. So, let us take one point here, their relative reactivity and interconvertibility. This is a general aspect, but a number of questions are coming pertaining to this particular concept, and it is the one of the best the logical supported the concept, and if you really they concentrate on this particular issue, I think number of the individual properties also can be easily guessed. So, here the if you take a carboxylic acid halide and the anhydride, third one, let us take 1, 2, 3 and 4. 4 derivatives I said, RCO, OR, fourth one RCO, NH2. Now, when you add water and see what happens, in the first 2 cases, just they react with water without any catalyst and all that, they undergo reaction, gives the carboxylic acid plus HCl in the case here. In this case, it is 2 carboxylic acids will come. No byproduct, the water is absorbed, anhydride opens up, you will get the 2 carboxylic acid. That is carboxylic acid plus another carboxylic acid, you can write like this. And in this reaction, the heat is liberated. Heat is liberated means what type of reaction they are? They are exothermic reaction, they are spontaneous. You doesn't require any heating or doing anything, just add water, immediately they form. So, this hydrolysis reaction is very vigorous. In fact, sometimes acid chlorides undergo some explosive type of the reaction also. That shows these 2 are more reactive than this one. Always in the nature, unstable compound forms stable. When this reaction I said it is spontaneous, this is stable, this is unstable or more reactive. So, acid chlorides and acid anhydrides are more reactive than the acid. Now, see the third one and fourth one, these 2 also react with water, but not just water, in presence of either with the acidic medium or with the basic medium, some catalyzing medium should be there, and then you have to heat it also. That shows they are not spontaneous. In the nature, you find that is why acids and esters, amides, esters and amides are freely available, where in the oils and fats, they are esters of glycerol. Glycerol will contain 3 carbons, 3 OHs on each carbon. Each OH is linked with OR like this. So, reversely in fact, the glycerol contain 3 carbons like this. In that 3 carbons, all this the acids are derived as a ester function. In fact, it is an ester function like this. So, all the OHs are esterified with the carboxylic acid. So, it is a triester. If you hydrolyze, that side you will get 3 carboxylic acid, this side 1 propane with triol, that is nothing but the glycerol. So, in the nature you find the oils and fats having this particular structure, means esters are quite stable, isn't it? So, esters are stable. Similarly, amides also, the entire proteins are nothing but the amino and the acid polymers, that is amino acids polymers, nothing, they contain a CONH, this bond is called amide bond, quite a stable one. So, all the proteins are stable, naturally available. Any compound it is available in the nature means it is stable, its reactivity is less, it is stable. So, if it is really like acid chloride highly reactive one, isn't it? Then it already would have been reacted with moisture or water and converted to some other compound. So, it is available in the nature means indirectly that is the compounds are very stable. These two compounds are more stable. When you react with water and with the catalyst temperature and all that, they will become into the acids plus alcohol. Here you will get acid plus ammonia. So, this is what hydrolysis. However, basically you can also have a, in acidic medium for example, the ammonia salt will be there. In basic medium if you use OH minus, if I use a, this will be in the form of metal salt, that is sodium hydroxide if I use for hydrolysis, sodium salt of acid, that is the practicality. But what happens when amide undergoes hydrolysis means one part will be acid, the other part will be ammonia. This part will be acid, that part will be the alcohol. This shows that the order of stability is from 1 to 4 order of stability is increasing. The more stable, more stable, more stable. So, the last one is much more stable. Reactivity is decreasing. The first one is more reactivity. So, the relative reactivity order. Reactivity order is 1 is more stable than 2, than 3, than 4. With reference to the carboxylic acid, if you take 1 and 2 are more reactive than carboxylic acid, you can also say like this. 1 is more reactive than 2 than carboxylic acid, than the 3 and the 4. The stability order. Stability order is 4 is more stable than the 3, than the 2, than the 1. So, reverse is the true for this the stability order. So, reactivity is acid chlorides are more reactive, stability comes amides are more stable. This can be also can be generally guessed also. Our body is made up of with the amino acid, that is polymers of amino acids means polyamides. So, amides are very stable. Unless it is stable, how we are sustaining, isn't it? It is not just reacting with water and so many chemicals exposure with nature and all that we are sustaining means the amide bond is quite a stable one. So, the amides are most stable one, and this is the order of the stability. The amides are more stable than esters, than the anhydride, than the acid chlorides. Acids come in between this 1, 2 and the 3, 4. This is what stability and the relative stability and the reactivity of these 4 compounds. Let us have another point, that is interconvertibility. That means one compound to other compound, how far they are ready to convert and all that. These 4 compounds, let me write in their examples. Okay. So, taking some acetic acid derivative, let us take this is acetic acid chloride, acetyl chloride. Okay. Let us call it as a 1, and the next member is a anhydride, acetic anhydride. Okay. Acetic anhydride means OCOCH3. This is acetic anhydride number 2, and then an ester, third one, acetic acid ester of C2H5, ethyl group, ethanol containing ester, third one, and lastly the amine of the RCONH2. This is acetamide, fourth one. So, let us remember these numbers also, as long as till the end of this chapter try to remember this. When I say the second member means it is anhydride, that is in specific ethyl, that is acetic anhydride. The compound 3 means, let us have this code, preserve it for some time. So, compound 3 are the derivative 3 is more stable means it is ester, specifically ethyl acetate, ethyl ethanoate, or acetic acid common name is their functional name. So, therefore, ethyl acetate, acetamide, acetic anhydride, acetyl chloride, these are all acid function we are using and naming. So, function nomenclature however, but systematically ethanoyl chloride, ethanoic anhydride, ethyl ethanoate, ethane amide, that is the systematic nomenclature. Now, let us see All the 4 react with water, gives the acid, that is called hydrolysis. Hydrolysis means any compound when you add water, it breaks up, if at all, if it breaks into 2 pieces, one side H, one side OH if I add, that is nolysis, breaking of the compound into 2 pieces, accepting one side H, one side OH, that is called hydrolysis. In the same pattern, if I use alcohol, add alcohol and break the compound into 2 pieces. So, I can extend this word called alcoholysis. When I add ammonia, ammonolysis. When I add a carboxylic acid, you can extend this to the acidolysis. Therefore, say the 1, 2, 3 are more reactive, they give the 4, isn't it? So, therefore, 3 can be converted to 4, 2 can be converted to 4 and 1 can be converted to 4 by adding water, ammonia. You need not to have any catalyst, just add ammonia. The NH2 minus happens to be the stronger base and replaces this old anion and shows this. What is the characteristic reaction means? A NH2 minus is replacing the alkoxide or acetoxide or halide minus. It is basically a nucleophilic substitution reaction. So, 1, 2, 3 undergo reaction with ammonia gives 4 means this reaction I can call it as a ammonolysis. Ammonia used, so ammonolysis. So, 1, 2, 3 undergoes ammonolysis and spontaneously gives the 4th compound. Similarly, 1 and 2 reacts with a ROH or acetic acid. So, I have given a ethyl. So, therefore, let me give the same specific example. Ethanol if I add, so C2H5OH is added and then they will react. However, in these 2 cases, even it does not require any catalyst, ethoxy group replaces this one. If it is in the sodium salt, wonderful reaction takes place because ready-made anion is there. Even with alcohol undergoes spontaneous. This reaction I can call it as a alcoholysis. Alcoholysis means cutting the compound into 2 pieces, adding one side H, one side alkoxide, you will get ester. Lastly, we have another point, that is 1 can be converted into 2. 1 can be converted into 2, isn't it? 1 can be converted into by adding the corresponding acid like RCOOH or with specifically acetic acid. You add acetic acid, then you get this one. This you can call it as a acidolysis. Acid is added, so acidolysis. The word itself is a novel. Acidolysis means which compound undergoes acidolysis is a one basic principle containing. Will the acidolysis 2 will be converted into 3? No. So, 2 is more reactive, isn't it? So, by acid, already acidolysis product it will not undergo acidolysis, isn't it? So, therefore, 1 undergoes acidolysis to give the 2, 1 and 2 undergoes alcoholysis to give 3, 1, 2, 3 undergoes ammonolysis to give the 4, isn't it? Now, vice versa is not possible, isn't it? So, you can claim like this, 1, 2, 3 readily convert into 4, isn't it? This is by called what? Ammonolysis. 1 and 2 converts readily into the 3 by adding the alcoholysis. 1 can be converted into the 2 by adding the acid. So, these 3 conversions are spontaneous. Reverse reaction, that is 4 to 3 or 3 to 2 or 3 to 1, these are all not possible reactions or not favorable reactions, otherwise you can say. So, 1, 2, 3 undergo ammonolysis fairly, 1, 2 undergo alcoholysis, 1 undergoes acidolysis. So, the questions can be framed, which of the following undergoes ammonolysis? Isn't it? That means 1, 2, 3 undergoes. 4 will not undergo ammonolysis because undergone ammonolysis and only derived. So, 4 will not undergo ammonolysis, 1, 2, 3 undergoes. Okay. Similarly, which of the following undergoes acidolysis means only 1 undergoes acidolysis to give the 2. So, on this 1 on alcoholysis gives what? So, one on alcoholysis gives the ester, corresponding ester is formed. So, therefore, a number of questions can be framed on this particular the direct reaction stability or interconvertibility. Then you can also go on another issue. The reason or what is the logic of this particular conversion, or why not the 2 undergoes acidolysis, or why not 3 undergoes that is acidolysis, or something like that. If I ask the question here, what is the group what is expelled? This is the group expelled. When I add ammonia, this group and this group can be successfully replaced by the NH2 minus. So, NH2 minus happens to be the strongest base than the ethoxide. So, C2H5O minus is the next stronger base. Then finally, this is the last but one is a acetate anion, CH3COO minus. Then comes the Cl minus. So, this is called what the group which can replace NH2 minus can replace this one. That is why NH2 minus is stronger base which can replace all three, and ethoxide is stronger which can replace these two. Acetate is stronger than Cl minus, so it can replace. So, which group can replace which are, if these 4 anions are given and asked, arrange there in their nucleophilicity. This order is called what? Replaceability order or nucleophilicity. Nucleophilicity. The order of nucleophilicity is like this. NH2 is stronger nucleophile than this one, In fact, nucleophilicity can also be taken grant in the other way as basicity. Several times it is equal, but not absolutely. So, the basicity, if these 4 are given, are asked to arrange in their basicity order. Basicity is nothing but almost equals to the nucleophile, except in few the conceptually. Base means OH minus reacts with H plus and forms water. In this, replaceability will not come. The nucleophilicity means there is a nucleophilic substitution like Rx minus. When you treat it with the Y minus is replacing the X minus. So, you will get Ry. So, the Y minus is now called as a nucleophile, and the OH minus reacting with H plus is just acid base concept. There is no replaceability. Obviously, base stronger, the base generally will be the stronger, except in the case of I minus. I minus is the stronger nucleophile and it is weaker base, that is the reversible one. Otherwise, you can generally take it stronger the base, stronger the nucleophile. In this 4, absolutely the 2 words are synonymous. You can use Cl minus is a weak base. Where from it is? It is from HCl. HCl is the strong acid, so Cl minus is weak base. Ammonia is weakest acid, so its anion is strongest base, isn't it? So, therefore, acetic acid is weak acid, its corresponding anion is strong base. Strong acid anion weak, weak acid anion strong. This is much more weak alcohol acid, so therefore, much more stronger. So, therefore, the order of basicity. You too can also see how best the outgoing property. Outgoing property is linked on the structure, that is the nature of this group. Here you see what is the outgoing group here? A nitrogen. Here this oxygen, halogen. Which best goes means lesser the electronegativity, outgoing will be less. So, the oxygen and the halogen, chlorine are more electronegative than nitrogen. So, they are all better outgoing group. That means they have a outgoing property means reverse to the nucleophilicity. Nucleophilicity means incoming property. Outgoing means leavability, or some books are specifically saying fugicity. Outgoing, leavability or fugicity is reverse to these 2 concepts. Basicity, nucleophilicity is incoming property. Stronger the base, better coming. NH2 comes easily into the acid, but leaves very poor. So, NH2 is a weak outgoing group. Strong incoming group, leaving group is less because it is electronegativity is less, therefore outgoing is less. So, based on minus I effect, the halogens and oxygens are stronger minus I elements, therefore they show better outgoing property, but this shows a later income. You too can apply the plasma effect also. Whenever the less electronegativity, the nitrogen shows more resonance or more plasma effect. So, obviously the carbon and the nitrogen several times it exists as a double bond. So, when it is double bond, how it will go out? No. So, the more the resonance, these are all higher electronegative elements. High electronegative elements will show less plasma effect, therefore mostly they will be single bond. So, therefore outgoing property more. So, you can apply the electronegativity of the element and you can see minus I effect. Consequently, you can also apply plasma effect. Among the oxygen and the chlorine, you have one more effect also. The oxygen belongs to the 2p series, whereas the chlorine belongs to 3p. So, therefore, overlapping between the oxygen and the carbon belongs to 2p, that is if at all if it shows plasma effect and in the resonance pi bond is formed, the pi bond between the carbon and oxygen both belongs to 2p. So, therefore, perfect overlapping. Here the chlorine belongs to third p. So, therefore, overlapping is less. So, this shows less mesomeric effect, therefore, the poor mesomeric effect. So, therefore, these two are more stable than the chlorine. If at all fluorine is there, it could have been, but fluorine always shows some exceptional behavior because of the more electronegativity, small size and all that. Let us not compare the fluorine here. The chlorine versus oxygen, oxygen and the carbon 2p, therefore more perfect plasma effect over the carbon and the chlorine. So, therefore, we justified the oxygen is a poor outgoing when compared with the chlorine. Among the oxygen and oxygen also you can have, this is a minus I effect attached with the minus M effect. This is minus I attached with plus I. So, therefore, this is the best outgoing over this. So, esters are, anhydrides are more reactive when compared with the esters. All these factors supported by this electronegativity, minus I effect, plasma effect and the 2p to 3p overlapping concept also you can apply. Finally, what we say is 1 is more reactive than 2, than 3, than 4, or 1 to 3 readily converts into 4, 1 2 converts into 3, 1 converts into 2. So, this side to that side shifting is easy, back coming is not favorable reaction. So, this ultimately shows that 1 2 3 are interconvertible, but not vice versa, only one side. From 1 to 4 they are convertible, 4 to 1 they are not convertible. In fact, that interconvertibility is not true word. They are convertible one sidedly, in fact, isn't it? That is the final statement from this reaction. Now, let us go to the individual member, that is an acid chloride we will take and discuss how this acid chloride reacts with the different chemicals and what are the important applications or the reactions of this acid chloride. So, let us take the first acid derivative, that is a acid halides, or directly you can take acid chlorides. A simple example is acetic acid chloride, that is acetyl chloride. Okay. So, systematically called, as I said, eth, 2 carbons are there, ethanoyl chloride, ethanoyl chloride, but it can be also called as a acetic acid, therefore, acetyl chloride, acetyl chloride. So, acetyl chloride is the common name, but systematically 2 carbons are there. So, ethanoyl chloride, ethanoyl chloride is the systematic name. How this compound is prepared and its properties, let us take preparation of this compound. As we have seen interconvertibility, this is the number 1. So, 1 cannot be prepared from 2, 3, 4. 1 can be converted into 2, 3, 4, but 2, 3, 4 cannot be converted. So, from the derivatives, other derivatives, you cannot prepare this one. The only one method therefore is take its original compound, that is a carboxylic acid, and go for its the derivative formation, that is either with PCl5 or with the PCl3 or with the thionyl chloride. There are 3 reagents are there. All these 3 successfully will replace this OH and you are going to get its corresponding acid chloride. In fact, this is the only one method we have, because the one is very reactive. The reactive compound cannot be prepared from the more stable compound. Therefore, obviously this is the only one prepared. But reagents are 3 reagents are there. Pentachloride, that is phosphorus pentachloride is there, phosphorus trichloride is there, and thionyl chloride is there. Not SO2Cl2, it is SOCl2 is called thionyl chloride, which can be used just like alcohols. All these 3 reagents can be also used on the alcohol. This is just referring. So, alcohol ROH can be converted to RCl. Similar to that, the acid, the OH also can be replaceable. In the alcohols, we can use another chlorinating, that is Lucas reagent, which is not applicable here. The Lucas reagent cannot convert RCOOH into the acid chloride. These 3 can be used. Now, let us take the properties or applications of these acid chlorides in the synthetic chemistry. Obviously, all the properties are nothing but the applications. In fact, the first property is hydrolysis. Hydrolysis. Acid chlorides readily undergo hydrolysis because they are highly unstable. In the nature, you don't get also acid chlorides are not available in the nature as such, because they are highly reactive. They react with water and spontaneously they convert into carboxylic acid and HCl. A lot of heat is generated. It is a highly exothermic reaction. So, the acid chlorides with water without any catalyst spontaneously converts into the carboxylic acids. They also can be converted into their derivatives, that is conversion into 2, 3, 4. I am using here the codes. What is 2, 3, 4? They are the other derivatives of the acid, that is acid anhydrides, acid esters, and the acid amides. So, acid chlorides readily convert because the other 2, 3, 4 are more stable. So, therefore, just by adding either with the carboxylic acid or its salt RCOONA. Best is always salt, as per the Williamson synthesis. A byproduct goes into the NaCl when you use this one. So, the reaction will become more easy. RCOOCOR, that is the anhydride is formed. And if I use alcohol, or best is a sodium salt of the alcohol, then you will get the RCOOR. This is the derivative 2, this is the derivative 3. So, you can also convert into its corresponding by adding the ammonia or sodium salt of ammonia, that is NaNH2, you get the RCONH2. This is nothing but the derivative 4. So, actually I have taken a compound 1, that is acid derivative of the acid chloride, can be converted into anhydride or into the ester or into the amide without any reagent. You see, either directly taking the compound, that is called acidolysis, or sodium salt or potassium salt or ammonium salt. If you take anhydrides, can be readily prepared. Only thing is byproduct changes, that's all. So, alcohol or sodium salt of alcohol, ammonia or sodium salt of ammonia, corresponding 2, 3, 4 derivatives can be readily prepared. This is a conversion of acid chloride into its derivative. In fact, the same concept can be used under the next property, that is the third property. So, one of the application for the acid chlorides is the third property, used as a acylating reagent. Acylating reagent. So, whenever you want RCO group in a compound, think about the acid chloride, that is the best reagent. You too can use the other compounds like anhydrides, esters also for acylating, but the number one reagent is definitely the more reactive, that is acid chloride. So, we have three types of acylating. We can acylating the nitrogen, N acylation. The one of the best example is here, aniline can be acylated. Aniline, when you treat it with acetyl chloride, acetic acid chloride when you add, so the aniline can acylate on the N. So, the COCH3 comes. This is called acetanilide, acetylated aniline, or has a common name acetanilide. Acetanilide. The nomenclature of acetanilide is that will become the main compound actually. Acetic acid is main compound. This is acetamide. This is phenyl group extra. So, call it as a N-phenyl acetamide, that is the acid is given a preference. So, acetic acid derivative of ammonia, acetamide with phenyl. So, N-phenyl acetamide is the IUPAC nomenclature, but acetylated aniline. So, it has got a acetanilide. We have one more example, a hydroxy containing ammonia, parahydroxy aniline. Okay. This is a reduction with nitrobenzene in electrolytic reduction. So, you get a OH, that NO2 is partly reduced to hydroxylamine, the OH is migrated to para. So, this particular compound parahydroxy aniline can be prepared in that way. So, that this compound when you treat it with acetyl chloride, see the OH also actually undergoes acetylation, but in preference with the OH and NH2, NH undergoes a reaction here. A question may be asked here, why NH2 reacted over the OH? In fact, if you add a reagents like sodium metal, first OH reacts because OH is more reactive than NH2. So, why the NH2 is reacted means the answer comes this way. So, I have taken a acetyl chloride, right? Acetyl chloride number is 1. If NH2 is reacted, it is converting into the fourth one. Okay. The other alternative, what is the answer for this one? The other alternative is so NH2 will be silent and the O is acetylated, OCOCH3. So, what is the derivative means it is 3. That means, if the question you put it in this way, if 1 is going to convert into 4, the option is 3. Would you like to convert 1 into 3 or 4 means 4 is more stable, that is why 4 is far. So, that means acid chloride would like to prefer to convert into amide rather than into, this is a RCOOR, ester it is. So, the ester and the amide both are in competition to form from the same compound 1. So, therefore, it will be always 4 will be in competition more preferable one. That is why the amino group is acetylated rather than hydroxy. If you add really the other chemical, that is acid base relation reaction neutralization type, if I add sodium hydroxide or sodium metal or something like that, the OH would have been react, that is an acid base concept. Here derivative concept it is. Acid chloride would like to become into amide rather than into a ester, that is the answer. That is why amino group is reacted. In fact, the product formed is a parahydroxy acetylated aminophenol is called paracetamol. Paracetamol. Paracetamol is a common name of this compound, para acetylated aminophenol, shortly called paracetamol. It is a wonderful the painkiller as well as a fever reducing reagent, and that drug, it is medicine. Paracetamol is traded under the different names like Crocin, Calpol or and so on, Dolo 650 and so on, different trade names are there, but basic principle chemical is used in that. Crocin is nothing but the paracetamol. It is prepared from the para-aminophenol acetylating, you will get acetanilide with a hydroxy extra group, that is called paracetamol. Similarly, you can go for the O acetylation instead of the N, you can go for the O acetylation. Okay. That means on oxygen acetylation can be done. So, let us take the another example. Now, let us take the second example B, O acetylation. Under the O acetylation, you can take phenol. Phenol is acetylated. when you use acetyl chloride, it becomes into O with COCH3. So, acetylation takes place on the oxygen. So, this is called a phenyl acetate. Phenyl acetate. Acetic acid is given preference. So, acetate, phenyl acetate or phenyl ethanoate. Phenyl ethanoate, that is systematic nomenclature. So, on the oxygen, acid group has come. Okay, this is called O acetylation. A good example is once again here. We have a carboxylic acid as well as OH. This is called a para-hydroxy benzoic acid, has a common name called salicylic acid. Salicylic acid. It can be prepared from the take phenol and apply the chloroform and KOH, you will get the salicylaldehyde, like that CCl4 will make this salicylic acid, or take phenol and carboxylate it, Kolbe-Schmidt reaction will give the salicylic acid. Now, salicylic acid is treated with the acetyl chloride. Once again question, among the COOH and OH, which is more reactive towards sodium hydroxide? Towards sodium hydroxide, COOH is stronger acid, this will react. But when acetyl chloride is added, hydroxy is reacting. Once again, the question can be exposed, why hydroxy group is reacting, keeping the COOH silent. Why means, if COOH reacts, you will get anhydride. Anhydride is number 2. If OH reacts, you will get ester. Ester is 3. That means, 1 would like to convert into 3, not into the other option is what? The acid reacted, for example, with acetyl chloride. What comes is a OCOCH3. This is anhydride, right? So, the acid chloride to anhydride means 2. Option is between 1-2 conversion or 1-3 conversion. Always 3 is more stable. That's why this won't be formed, this will be formed. So, hydroxy group, though it is less reactive towards sodium hydroxide, but with this acetyl chloride, the COOH will be silent, OH is reacting. Because of this derivative 1-3 is more successful reaction conversion rather than 1-2 conversion. So, therefore, the OH undergoes that is esterification and you are getting a ester it is. This is commonly known as aspirin. Aspirin is also wonderful medicine used in the headache and the different ache, the controlling. It is nothing but the acetylated salicylic acid. So, aspirin contains COOH, that is why the hyperacidity patients are not advised to take aspirin, because it slowly releases this acid and creates some ulcers and so on. But the aspirin is found to be one of the best the anticoagulating agent or blood thinner. So, therefore, heart attack controlling one of the indirectly it is used. So, the aspirin is used no doubt for the anti that is headache painkiller, but it is also advised in the case of heart attack patients, because it is a anticoagulating agent, it is working as a very good supplement for the particular heart patients. So, salicylic acid acetylation will give acetylated salicylic acid, commonly known as aspirin. It is a painkiller drug. Let us take one more acetylating, that is a C acetylation. Acylation on the carbon. One of the best reaction we know is benzene when treated with the acetic anhydride. AC2O stands for the acetic anhydride, AC stands for the CH3CO, right? So, it is twice, that means CH3CO twice, CH3CO, CH3CO attached through oxygen. So, this is a short form of this acetic anhydride representation. So, acetic anhydride when it is treated with benzene in presence of some Lewis acid like aluminum chloride anhydrous, the acetate anion will be held with this aluminum chloride. This carbocation generated attacts as an electrophile. So, this is an electrophilic substitution reaction known as a Friedel-Crafts. Friedel and Crafts. Friedel-Crafts acylation. If Rx is used, R comes, that is called Friedel-Crafts alkylation. See the mechanism once again. Any Lewis acid, if you use, that holds the anion part, and this electrophile introduces in the place of hydrogen. So, you will get acetylated benzene, acetylated benzene, that is acetophenone, a ketone is formed. This reaction is a well known reaction in the benzene chemistry. Friedel-Crafts acylation, RCO group, depending upon the R, the different types of the ketones can be generated in this particular reaction. This is obviously a acid group coming on the carbon. So, I said acetylation can be on the oxygen, can be nitrogen, can also be on the carbon. So, acetylating acetyl chloride, acetic anhydride or acetyl chloride. In fact, we are using a acetyl chloride, isn't it? So, that is a ACCl or a CH3COCl. Either one can be used. This is the number 2, however, but the number 1, if I use the much more better reaction you get. So, we use either acetyl chloride or acetic anhydride in the Friedel-Crafts acylation. So, anyhow the acetylating capability, if I discuss, definitely number 1 will be the better reagent over the acetic anhydride number 2 reagent, isn't it? So, both can be used. Even esters can also undergo the acetylation type of the reactions, but very less. So, acid chlorides happens to be the number 1 reagents to acetylating the reagent. Now, let us take some specific reactions of acid chlorides, that is a 4th reaction. There is a name reaction called Rosen-Mundt reduction. Rosen-Mundt reduction. This is acid chlorides reacting with the hydrogen gas in presence of a specific catalyst like palladium supported by the barium sulfate in presence of quinoline, an organic solvent. This particular, the mixture of palladium with barium sulfate and quinoline is also known as a Lin-Lars catalyst. Lin-Lars catalyst. The catalyst we used in the case of converting the triple bond specifically into the double bond using the same catalyst and the hydrogen gas. Ine can be converted into ene selectively. The same reagent I am using here, but converting the acid chloride into the aldehyde. Here also the question comes, in fact, the aldehydes are more reactive to undergo further reduction to give the alcohols, but the reaction is so specific, it is catalyzed, okay, but because of the sulfur present in the extra catalyst, this is catalyst actually, this is a decatalyzing agent actually, this works as a poison on the catalyst. Therefore, the catalyst takes place only one step, not the second step, it stops at this level, not the further. In fact, only palladium and hydrogen is used, or nickel and hydrogen is used. Definitely you will get first step aldehyde, then successfully reduces to get the alcohol, but here only up to aldehyde is formed. The mechanism can be explained. Hydrogen is added on this one, you will get a first RCH, a OH is formed with Cl, and the OH definitely what it will do is this pair can be shown like this and the Cl will go out. So, therefore, HCl will be removed and you will get the corresponding aldehyde by minus of HCl. So, you get the HH addition just like catalytic hydrogenation, one-sided hydrogenation, you will get the OH and H, the H and H will be removed and the double bond, the Cl will go out, HCl will go out. So, you will get this aldehyde, but there the reaction stops. In fact, the acid CO, that is the regular reduction, RCOCl reduction with lithium aluminum hydride. Okay, if I use lithium aluminum hydride, the reduction first you will get the aldehyde. The aldehyde undergoes further reduction to give the RCH2OH. In fact, this type of reduction, even other compounds like carboxylic acid, we have seen acids, acid chlorides, acid anhydrides and esters, all the 4 compounds will give this one. except the last derivative, that is acid amides with lithium aluminum hydride, they will give 1 degree amine. There also we discussed NH2 is a poor outgoing group, therefore, it will not leave out and it will stay back in the form of 1 degree amine, we get it. So, all these will be reduced to 1 degree amine. This particular reduction, that is acid chloride to selectively to give the aldehyde using this particular Lindlar's catalyst and hydrogen gas. The hydrogen gas will not constitute into the reagent, this is separate. Hydrogen RCOCl with hydrogen in presence of Lindlar's catalyst reducing to partially to give the aldehyde is known as Rosenmund's reduction. Rosenmund's reduction, specific reduction. Acid chlorides with commonly with lithium aluminum hydride or sodium borohydride, they will give the 1 degree alcohols. So, let us go for the next properties of the acid chlorides. Fifth one, this is the reaction with a Grignard reagent. RMX is known as Grignard reagent. This Grignard reagent has a number of applications, but one of the best application of this RMX is with acid chloride. It shows a double reaction, you can also remember like this. It shows a double reaction. So, you take RCOCl, add RMX. The R adds on the C, magnesium adds on the O. So, in fact, a unstable compound is formed like this, O minus with a MgX plus with a S1 Cl with 1 R. So, as I said, O minus and Cl combination cannot sustain, therefore, O minus will come back and expelling the Cl. So, therefore, what comes is now the RC double bond OCl. This is a ketone, in fact. A ketone is formed, but this ketone is once again more reactive towards RMX. In fact, much more reactive than the acid chloride, because here the double bond is delocalizing, it is a static double bond, therefore, much more favorable for the nucleophilic addition. Therefore, one more RMX is going to add. So, R adds on the carbon, magnesium adds on the O. So, you will get already 2 R's are there, one more R. So, therefore, 3 R's will be there, O will become into the salt, OMgX is formed. This on hydrolysis. Hydrolysis can be with water alone also, or water plus acidic medium, that is acidic hydrolysis is more favorable, it cuts into H and the OH. So, we get an alcohol containing a 3 R's. Of these 3 R's, 2 R's are from the RMX, we got it, 1 R original 1. So, let us take R1. So, this R1 is the only one which is original 1. If I take R2 here, so this is the R2 and this is also R2. So, 2 R2s are from the RMX, 1 R original 1 with in addition to the 2 R's. So, tertiary alcohol, a 3 degree alcohol is finally formed. In this reaction, we cannot stop the ketone level. It's an in fact indirectly it's a drawback. Can you prepare ketones by this reaction means somebody may say, so I will take 1:1, what happens? 1:1 if you take also, all cannot react at a time, isn't it? Little part of this little part will react in the first stroke. The ketone formed will take back the RMX once again and you will get maybe mixture, you will get tertiary alcohols and the ketones mixture, but never you will get the whole ketone, though you take 1:1. Mathematically, it is you can claim 1:1 if I take only ketone will come. That is not correct. Practically what happens is the ketone formed is more reactive than acid chloride. The moment a part ketone formed, it will take the RMX and goes into the tertiary alcohol. Therefore, inevitably you will get a tertiary alcohol, not whole, but maybe mixture of these two. So, therefore, by controlling 1:1 is not the correct method, but we have another method to get the ketones also, we have another method. Now, in this method, let me explain once again. An acid chloride, if you add RMX, better always 1:2 you take, definitely you will get tertiary alcohol, or you may take excess of RMGX, then definitely first you will get ketone, then again reacts and tertiary alcohol. Therefore, I claim this reaction as a double reaction with RMGX, 2 times reacts. One time reacted product is the ketone that again reacts, and you will get this time both the reactions happens to be a nucleophilic addition first, but this up to this what happened means it looks like nucleophilic substitution. Cl has gone, R has come. See here, Cl has gone, R has come. What is this type? Nucleophilic substitution. That is wrong actually. Nucleophilic addition takes place and then undergoes a removal of the magnesium chloride. A ketone is for 2 times it is nucleophilic addition only. The nucleophilic addition on CO is not that favor. That is why step 1 is not that reactive. Step 2 is much more reactive than the step 1, because carbonyl compounds nucleophilic addition is faster reaction than acids and acid derivatives, because they are delocalized double bonds. So, therefore, that is more reactive than the step 2 is faster reaction than the step 1. But finally, you get a tertiary alcohols in this double reaction is taking place. So, you can prepare ketones. In fact, ketones can be prepared, but not using the RMGX directly. Given RMGX, what you do is, or you better take a Cl, RMgCl I will take, add the cadmium chloride. This will give the 2 moles of RMGX react with the cadmium, R2CD is formed. This is a just like a metal with carbon, that is called organometallic compound. Even here also metal cadmium is linked to the R directly. So, this is also a organometallic compound, OMC we say. OMC stands for what? Organometallic compound. Both are organometallic compound. Relatively, this is less reactive than RMGX. Therefore, the more reactive one I converted into the less reactive organometallic compound. The magnesium converts into the magnesium chloride. Okay, 2 magnesium chlorides. Now, this you use on the acid chloride. Acid chloride reacts with R2CD. Slowly reaction takes place. Now, one of these are now almost replacement, as I said, it looks like replacement, but actually addition, elimination you will get. So, this R will be now getting into a ketone, and you take 2 RCOCl, and the cadmium will take this Cl, will be again cadmium chloride is formed. In fact, if you add up this reaction, cadmium chloride can be cancelled, and R2CD is cancelled. What exactly I am using is RCOCl and RMGX. So, Grignard reagent and this one reacting into ketone, but the reactions we have to do separately, not in one flask. So, first RMGX you convert into the R2CD. Let this organometallic compound cadmium, dialkyl cadmium is formed. Then only you add it to this one. Net reaction is nothing but the Grignard reagent only I am using, but converting into another organometallic compound, then add it, you will get the ketone. The reaction stops there, because ketones are not reactive towards this RMGX, the organometallic compounds. Then we take another reaction. This is also very popularly known, that is known as ARNDT, Arendt Eistert synthesis, popularly known as AES reaction. AES stands for the Arendt Eistert synthesis. In this synthesis, a carboxylic acid if I take, which will be converted into a RCH2COOH. That means an extra CH2 is brought into the acid. So, acetic acid if I take, propanoic acid if I take, butanoic acid. So, 1 carbon extra acid can be prepared. Therefore, specifically just like Williamson synthesis used for the ether preparation, like that this is specifically I am calling it is a synthesis reaction. In the organic chemistry, the synthetic the purpose containing reactions are little more useful than the ordinary simple properties. This is a synthesis of a carboxylic acid. Synthesis involves a readily available smaller compounds, a cheaper rate generally, will be converted into a rarely available or little more costlier compound or relatively bigger compound if you can prepare. Such a type of the conversions are said to be synthesis. So, we are perfectly doing a synthesis in this reaction. Smaller compound is converted into bigger compound. This reaction involves, first you convert this into the acid chloride by using the PCl5, let us say. First the acid is converted into the acid chloride, then another reagent subsequently, not at a time, subsequently you use a CH2N2. This is called diazomethane, a gaseous compound prepared or trapped in the ether, and that ether is added, diazomethane. Then finally, a moist silver oxide is added, moist silver oxide Ag2O. Silver oxide in presence of water, that is not totally, it just moist silver oxide is added, and then that works as a partly hydrolyzing reagent that converts into this one. So, let us see what exactly happening in these three reactions, and the first conversion in fact reacting with RCl5 converting into acid chloride is no more a name reaction. That make acid chloride comes first, that reacts and then undergoes a rearrangement also involved in this reaction called Wolff rearrangement, and how the exact mechanism goes, let us concentrate. So, let us say the mechanism of how the reaction proceed. First, as I said, RCOOH, when I treat it with PCl5, you will get the RCOCl. This is no more a Argentine synthesis, a part it is actually. But this compound, when I treat it with CH2N2, CH2N2 will have a structural formula like this. A plus will be there, 2 hydrogens will be there, a minus will be there. Okay, right. Now, here 2 molecules are consumed. Okay, 2 molecules of diazomethane is consumed. One of the CH2 liberate the H for that one, that will become CH3 plus Cl. One of the byproduct is CH3Cl, where from it is formed 1 CH2 plus hydrogen of the other CH2 will become CH3 plus Cl, CH3Cl. So, 1 nitrogen also will be expelled out, but 1 CH2 without hydrogen is stick to this RCO. So, you have a CH with N triple bond N plus and minus is formed. This is the one first intermediate you are getting. This is not the compound, an intermediate compound is formed. So, this is called acid, okay, right, carboxylic acid, carboxylic acid. The next is acid carboxylic acid chloride. Then step what you get is, this is called diazo ketone, one side alkyl, one side diazo is there. The diazo containing RCOR. So, we call it as a diazo ketone. Common name it is diazo ketone. This diazo ketone undergoes a loss of the 2 electrons are withdrawn by the nitrogen. So, N2 molecule, a neutral molecule will come out, minus of N2. Then this carbon will become some unusual type of structure. A carbon will have 1 hydrogen, 1 minus charge, but 2 electrons are taken out, therefore, 1 plus also obviously should be formed. So, 1 minus is there, 1 plus is there. This is structurally something wrong. So, therefore, let us rewrite this structure as a RCO, 1 hydrogen, okay, but this pair, the minus charge I write as a lone pair, this plus I put it as a box, so that vacant orbital is shown. A deficiency and excess on the same carbon having a lone pair hybridized sp2 hybridized, vacant orbital need not to hybridize, 3 hybrid orbitals are there, sp2 hybridization. This is called a carbene attached with acid group, common name acyl. acyl carbene is formed. The acyl carbene undergoes, say now, one R with 2 electrons will jump onto this vacant, because this deficiency causes much more instability rather than excess. Therefore, R with 2 electrons, R minus, undergoes a shift. This is actually a rearrangement step, right? So, let us use this R with rounded up, maybe applied to the rearrangement concept. So, R minus is undergoing within the molecule shuffling, nothing is added or deleted, but rearranged. So, this step we call it is a rearrangement step in which this R is shifted, immediately the lone pair is used to make a bond. So, therefore, C double bond O with double bond C with one hydrogen and R, shifted R. So, this is called a ketene with R. So, this is called alkyl ketene. This is also another intermediate compound. So, one intermediate is diazoketone, second intermediate is acyl carbene, third intermediate is alkyl ketene. This alkyl, it's not ketone, it is ketene. CH, this side also carbon is there, it is alene, but so O's it is carbon dioxide, one side CH, one side O is called ketene, alkyl ketene it is. This alkyl ketene is added water. This water is not from the regular water or not by acidic medium, basic medium water, that is called hydrolysis. It is hydration taking place using this moist silver oxide with the help of this Ag2O. So, only small quantity of water is added, otherwise both will cut up and this will become alkane, this will become carbon dioxide. So, there is no point in making the compound. So, therefore, just add water HOH, so that this will become into C double bond O with the OH and the CH with another hydrogen CH2, the R. That means RCOOH with an extra CH2 gain. So, that is nothing but the RCH2COH. In fact, if I start with RCOOH, this is RCOOH with extra CH2. So, this CH2 is obviously coming from the diazomethane. So, diazomethane carbon, if it is labeled as 14, notice that this labeled carbon comes here, labeled carbon comes here, labeled carbon comes here, that will become CH2. That means labeled carbon will be here in the middle. So, neither added backside or added front side. Generally, a reagent which is added, either front side or backside goes. But in this case, what happened? This added carbon has come exactly in the center of the R and the COOH, just like stuffing the case. So, the CH2 comes in between the R and the CO. So, as it is shown here. So, first CH2 comes, then R comes from this side and back up. So, therefore, the CH2 unit comes in the center. So, R2 CH2 means this CH2, if it is 14 is there, that question has come once. So, the C14 comes here, okay, right, not the last carbon or the first carbon. In between carbon will become into that labeled carbon, goes to the middle. So, this particular type of the synthesis is known as what? Arndt Weierstrass synthesis. In this reaction, a smaller acid is becoming into the bigger acid. There is another reaction, that is bigger acid to the lower acid also. But instead of acids, generally we use esters in that reaction. So, let us use in the esters chapter that particular type of the conversion we will see.